Chapter 1, Section 6 is on other types of equations. So if you'd please turn in your book to where this section starts, we will get our lesson going. There's a lot of examples in this section. Okay, some of them more difficult than others, so make sure that you take good notes down. 1.6 begins on page, let me get there, 121. All right, so when we work with polynomial equations, they're going to come in various kinds, sizes, degrees, and so on. We've already been working with solving some quadratics. Okay, so we've done quite a lot of work with that in section 4. The ones that we look at today, many of them are going to be a higher degree than degree 2. For example, the one on this slide here, we have 9x to the 4th power minus 12x squared is equal to 0. This one has just 2 terms in it. There is a difference or subtraction between them. So in solving this one way you might want to check it is if in fact these 2 terms are both perfect squares, we could do that factoring of difference of perfect squares. The 9x to the 4th power is good to go. That'd be 3x squared times 3x squared. But when we look at the second one, the 12x squared does not fit. So that quick pattern of factoring is not going to get us anywhere. So then, being there's only 2 terms, just investigate and see if you can factor out a number and or variables. So between a 9 and a 12, we can factor or pull out a 3. And with our x's, we can pull out or factor out x squared. What remains then is 3x squared minus 4. To finish solving, we look at both of these factors that we have made and determine or figure out what x value would make 0 for our equation. So the first one, if in fact we put a value of 0 in for the x, we would have 0 for a value of our equation. The second one, the 3x squared minus 4, it still has a squared term in it, so check and see if you can factor it some more. This particular one doesn't. Again, it's not a difference of perfect squares, so you're going to have to do a little bit of work in order to figure out the solutions for x here. So off to the side maybe, take the actual factor and set it equal to 0 and solve. Now once we get it to here where x squared is equal to 4 over 3, what we can do at that point is extract our squares. So x is going to be plus or minus the square root of 4/3. Part of that solves. Okay, square root of 4 is 2, but the square root of 3, which is the denominator, does not solve. Now if you remember back to our discussions earlier in the class, you cannot leave a radical in a denominator. So in order to rationalize that or get the radical out of there, multiply root 3 by itself. What you do to the bottom, you must do to the top. And that's going to give us plus or minus 2 root 3 over 3. Okay, so the solutions for this factor, there are 2 of them, positive or negative 2 root 3 over 3. The next one, we looked at this when we were doing our preview chapter and some review of factoring. Remember when there are 4 terms like this one in descending order. We have cubed, squared, x to the 1st power, and then x to the 0 technically, or a constant. What we're going to look at is factoring by grouping. All right, so I put a physical line in there to group my front half and my back half, and see if there isn't any way that you can factor or break those 2 halves down. In the first part here, I can factor out an x squared, leaving x minus 5. In the back half, I know I can take a 2 or a negative 2 out, but I want to try to match this x minus 5 chunk. So if I pull a negative 2 out, I'm going to get an x minus 5 remaining. So both the front half and the back half ended up with a factor of x minus 5, so I can factor or pull that out of both. And then my second factor is the remaining pieces of those halves. Now I find my solutions. So my first factor, x minus 5, has a value of 5 as a solution or a 0. My second half, x squared minus 2, is still a squared term. It's not a difference of perfect squares. So again, off to the side here, do your math steps to find a solution. Okay, extracting the square root of both sides now. X equals plus or minus root 2. So again, we're going to have 3 solutions total, a 5, and a positive or a negative root 2. This one happens to be example number 3 that's in the text. I solve problems of this kind differently than what the textbook did, so I figured I'd offer you my method as well. Pick whichever one makes more sense to you. When I look at this one, it is a trinomial. It's a degree 4, and then a squared, and then a 0 power, which actually is still more or less in quadratic form, and you can think about or try to do a factoring with this. So just like you would factor an x squared trinomial, x to the 4th can break into an x squared and an x squared. Then still look at your back digit, your constant, and figure out how to break it into 2 numbers or 2 factors that will combine and give you a negative 3. So if I go with negative 2 and negative 1, look at my inside, outside for my FOIL. You can see there you're going to get that negative 3x squared in the center. So this is a way to factor that particular polynomial that they gave us. Now both of our factor pieces are squares, so check them to see that if you can factor some more. Now that first one, x squared minus 2, we just got done solving that one in the previous example. So I know that my solutions for x squared minus 2 are plus or minus root 2. My second factor, x squared minus 1, this is a difference of perfect squares. You can factor it some more. And from that then I can see that I'm also going to get a positive 1 and a negative 1. So plus or minus 1 are also solutions. I have 4 zeros or 4 solutions for this polynomial. Let's take a look at another one like that. Okay, so this one is checkpoint part B on the bottom, page 122. So we have 9x to the 4th minus 37x squared plus 4. Again, with the 4th power and then the 2nd power in here, I can consider trying to break this with factor pairs. Now you're going to have to play around with this because the 9 as the lead coefficient has a couple of options. You can either break it into a 1 times 9, or you could break it into a 3 times 3. You're going to have to play around with that a little bit. Likewise, the 4 at the back, you have options there too. 1 and 4, 2 and 2. So when I start looking at these, I see that I'm going to be working with 9s and 4s, and I need to get to a negative 37 in the middle, which is kind of a large number. So I'm going to, at least to start with, if I'm checking or trying stuff, I'm going to leave the 9x squared and the x squared as the breaking factors for my 9x to the 4th. And then I'm going to pair the 4 with the 9, because that gets me to 36. I'm almost at my 37. Since my 4 is positive, but my 37 is negative, I know both of those numbers for my 4 have to be negative, negative 1 and negative 4. If I check, I do in fact end up getting my negative 37 in the middle, so I've successfully factored or broken that original polynomial. Now both of these factors again are squared terms. See if you can break them some more. This time both of them fall into a pattern for a difference of perfect squares. So 3x minus 1 and 3x plus 1, and then an x minus 2 and an x plus 2. So my solutions are, I'm going to get a 1/3 and a negative 1/3 for those two, a 2, and also a negative 2 for this one. We're going to be taking a look at equations that have radicals in them as well, or square root symbols in them. Some of you guys really like steps to processes, so I've attempted to put some steps to guide you on this slide. If you'd like, copy them down, so hit pause for a little while, and then we'll go on to an example where you can put the steps into motion. All right, so this one you can clearly see has a radical in it. And again, according to the steps, you need to isolate that radical sign, and then we know we can get rid of a radical sign by squaring it. But you have to get it down to just that chunk and everything else on the other side of your equation in order to apply that. So, in looking at this, I'm going to move the 2. Then I need to divide by -1 to get rid of that negative sign out front. So now I have the square root of 40 minus 9x. On the right-hand side, I'm going to have a negative x plus 2. So I have my square root isolated. I can go ahead and square both sides now to get rid of that. So squaring my left-hand side, it's going to leave me with 40 minus 9x. Now squaring the other side, squaring a binomial means that you're going to have to FOIL. So off to the side here, I'm going to do that little bit of work. I have a negative x plus 2 times another negative x plus 2. So negative x times negative x is x squared. Then I have a negative 2x and another negative 2x for my inside-outside. And 2 times 2 is 4. Simplifying. So when I square the right-hand side, I get that expression. So let's put it in place. So if I'm going to solve this, I'm going to bring everything over to the right-hand side. So I want 0 on the left. And I'm choosing to put everything over on the right-hand side this time because my x squared term is already positive over there. You can bring it all over to the left as well, but then you'd have to remove the -1 and blah, blah, blah. So I'm moving everything to the right to keep that lead coefficient a positive. So that means I'm going to have to add 9x. So the x squared, there was nothing to combine with. My negative 4x and the plus 9x will give me positive 5x. And I also need to move the 40, so that's going to be a minus 40 to both sides, and I get a negative 36. All right, I have a quadratic. You've got several ways in which you can solve this or factor this. I'm going to check it first to see if I can't do it the fast way with factor pairs. And a 36 has 9 and 4 as factors, so I'm going to work with them. A positive 9 and a negative 4 will give me my positive 5 in the middle and my negative 36 at the end. Solutions then. Negative 9 and 4. Now, this was one of those that, you know how we talked about in previous sections that sometimes what appear to be solutions of equations are not exactly solutions to equations? You always need to perform a check and make sure that the numbers actually follow through and work. If we were to go ahead and check these numbers, okay, let's check the negative 9 first. We'd have a negative 40 minus a 9x. Okay, so that'd be plus 81. Add 2 equal to negative 9. Okay, so a negative square root of 121 plus 2, negative 11 plus 2 equal to negative 9? Sure it is. Negative 9 works. But let's try the 4. So we've got the negative, put 4 in this time, 40 minus 36, add 2 equal to 4. Okay, so I've just plugged the 4 in for my x's. I'm going to get negative square root of 4 plus 2 equals 4, or negative 2 plus 2 equals 4. That does not work. Okay, so 4 is one of those solutions that's called extraneous. Remember that from earlier on? So even though it looks like it's a solution, there ends up only being one actual solution for this problem, and it is the negative 9. All right, I threw this one in from our exercises. It has 2 radicals in one problem, so I wanted to show you the work that's behind solving one of these. There's a lot, okay, so give yourself a lot of room. If you're kind of at the end of a page, you might want to start a new page with this one. We still have to follow that process of isolating a square root so that we can square sides and eliminate the square root symbol. But we're going to have to do it twice here. We're going to have to eliminate one first and then the other next. So I'm going to first of all isolate this term. So I'm going to add the square root of 2x plus 3 to both sides. So now I have, I'm going to move way over this, I'm going to fill up the board with this problem, so hang in there. You might want to just watch all the way through and then go back and write some problems down. I guess I got rid of that. That should be an equal sign. 1 plus 2x plus 3. Okay. Now I can get rid of the 2. All right, so I'm going to divide both sides by 2. So now I have a square root, and I have 1 plus square root of 2x plus 3 over 2. I'm going to now be able to eliminate one of my radical signs. I'm going to square the left-hand side. If I square the left-hand side, I have to square the right-hand side. So let's do just that. Squaring the left-hand side gives me just x plus 1. Squaring the right-hand side is a little bit more involved. The bottom's okay. Square of 2 is just 4, but that top, I have a 1 plus root 2x plus 3. I'm going to have to FOIL that. Okay, so off to the side here, and I'm probably going to have to erase this later, so get it down first. I have to take this times itself. 1 times 1 is 1. Outside, I have 1 times root 2x plus 3, so I'm going to get a positive root 2x plus 3. Inside, I have another 1 times root 2x plus 3, so I'm going to get another positive 1 times 2x plus 3. And then the back. When I do the last terms, I'm taking a root times itself. So remember, that's just going to result in giving me the amount that was underneath the radical. All right, combining like terms in the middle. I have 2 square roots of 2x plus 3. My 1 from the front and my 3 from the back can combine. My 2x does not have anything to go with it. So putting all this stuff together results in this piece. Okay, so my numerator is going to be that whole mess. I have 2 square roots of 2x plus 3. I have a 2x, and I had a 4 when I squared that term. Okay. Take a couple seconds to take in all that math. I am going to erase that foiling that I just did. Whoops, and I've got to rewrite this. I forgot my x. Okay. All right, this is gone. Okay, so once I get there, I'm going to get rid of my denominator. Okay, so if I multiply both sides by 4 right now, I'll get here. Now again, I have a radical still remaining. I'm down to 1 though. So if you shift and move everything else to the left, I'm going to be able to eventually isolate that 1 and get rid of it. So I'm going to subtract 2x from both sides. And I'm going to subtract 4 from both sides. So now I'm here. I can come back here and get rid of that 2. Divide both sides by 2. And I'm looking at, come up here, x is equal to the square root of 2x plus 3. All right, I have that square root isolated. If I square both sides right now, I'll have an x squared on the left and 2x plus 3 on the right. Get everything together. So x squared minus 2x minus 3 is equal to 0. I have a regular looking quadratic. Crazy enough, it has simplified down to this. A minus 3 and a plus 1 will finish this off. Solutions. 3 and negative 1. Now for time issues, You can check both of them to make sure that neither of them are extraneous. And this time, I'll just give you that one. They both work. What if we end up with rational exponents? Okay, what if you end up with a fractional exponent is what that says. You're going to rewrite the equation in radical form. You might have to look back on page 22 for how to do that. Then you'll be able to clear the root and lastly just finish solving the equation that you're left with. All right, these take a little bit of playing. Okay, let's take a look at one together. We have x minus 5 to the 2/3 power. Now, if you look back on page 22, it gives us the rules for these exponents and how to rewrite from exponential form to radical form. This 3 becomes the root. Okay, so if I were to rewrite this with a root symbol, that tells me which root I would have. The top number just stays attached to the factor. Okay, so x minus 5 squared would stay here. Okay, so all I did was rewrote from one form to the next. I haven't solved a thing. Now if I have a cubed root, in order to get rid of a cubed root, I'm going to cube both sides. Just like if you're getting rid of a square root, you square both sides. If you need to clear or get rid of a cubed root, you're going to cube both sides. So if I cube the left-hand side, it's going to leave me with what was underneath the radical. And now I have to cube the right as well. Okay, so the x minus 5 squared, now we can FOIL that. We get x squared minus 10x plus 25. And then 16 to the 3rd power gives us 4,096. Bring that over to the left. Join it up with everything else. And I get this quadratic. All right. You very well may be able to factor this one. If you find factor pairs of 4,071 that are 10 apart, go right ahead. For me, this one was one that I kind of punted and went with quadratic formula instead. Just because I figured if there were real solutions or solutions to find the quadratic formula, would get it for me anyway without spending all the time trying to figure out the factor pairs for that big number. So negative b plus or minus b squared minus 4ac, not AA, AC, all over 2a. Okay, so negative b plus or minus b squared is 100. 4 times a times c. And then all over 2 times 1, or 2. Okay, simplifying. Now negative 4 times positive 1 times negative 4,071 is a positive value. Oh, I forgot to write that number down. Give me a second and I'll punch it in quick. Well, I guess I can figure out what it must have been. It must have been 16,284. Let me just double check. 4 times 4071. Yep, 6284 all over 2. Adding the 100 to that, 16,384 over 2. And by golly, if you take the square root of 16,384, it actually turns out to be a nice number. It's 128. So now 10 plus 128 over 2 is 138 over 2, which is 69. 10 minus 128 is negative 118 over 2. We get negative 59. All right, what if we have rational equations? In other words, we have fractions in our equation. You know that in order to be able to add or subtract with fractions, we have to have a common denominator. So take a look at the denominators that we have. One of our terms has an x, another of our terms has an x plus 3, and the last term has a 1. So our common denominator is going to be an x times an x plus 3. So what we can do is get that common denominator, and once all the denominators are a match, we can focus on the numerators to finish solving our equation. All right, so if I'm going to multiply everything by my common denominator, in this first one, the x will take out that part. I still need to multiply 4 times an x plus 3. I'm going to get 4x plus 12. In my middle one, my x plus 3 will cancel, so I end up with 2 times x still. On the right-hand side, nothing's going to cancel, so x squared plus 3x has to be multiplied by our negative 3. So I get a negative 3x squared minus 9. Bring everything together. I'm going to come to the right this time so that my x squared term becomes positive. So over here on the left, did I say go to the right? If I did, I don't mean that. I'm coming to the left. That'll be a positive 3x squared over here. I have a couple of x's to combine. 4x and 2x make a 6x. And then I want to bring my 9 over as well. And I get 21. Oh, here's my mistake. Sorry. I got to back up a little bit here, you guys, because I don't want to start the entire video over again. Clear this back. When I multiplied right here, I should have had an x squared plus 3x, which changes this just a little bit to a negative 9x. And that's where I went wrong. Now let's get our stuff all together. The negative 3x squared is still coming over. But now my negative 9x comes over and combines with my 4x and my 2x. So 15x all together, and there is only one constant. That 12 is by itself. All right, that matches my notes. Now I need to factor this. Again, you could go right ahead to parentheses if you want, but I notice in this one, I can pull a 3 out of everything. So I'm going to start with that so that I have smaller numbers to work with, and it's easier to factor. So x and x, positive 4, positive 1. So two solutions, negative 4, negative 1. Again, you're going to want to check to see if these are extraneous. The only thing that we really have to worry about as far as undefined stuff is making sure that we don't end up with any zeros as denominators. In looking at the x and the x plus 3 denominators up top, neither of these are going to hurt that, so I think we're pretty good. Absolute value equations are also reviewed and dealt with in this section 6. Remember that the absolute value represents a distance from 0, and there's two sides of 0 to consider. So when you're solving absolute values, you're always going to have to solve two situations. Let's start out with an easy one to review. So the absolute value of x minus 3 is equal to 9. Okay, if you recall from the past, one of our situations is covered by the actual thing that you see minus the absolute value bars. Now to cover the other situation or the other side of 0, you need to set the x minus 3 or the absolute value expression equal to the opposite of the right-hand side. And now we just solve. So x equals 12 will work. And x equals negative 6 will work. Let's take a look at a little bit bigger one. Okay, same situation. My absolute value on the left is isolated. There aren't any other numbers attached to it. So at this point, I can set up my two situations. I have x squared plus 4x is equal to 5x plus 12. My other situation is to take my absolute value expression and set it equal to the opposite of the right-hand side. All right, so solving. Bring everything over to the left-hand side over here. So minus the 5x and minus the 12. And it's a quadratic, so let's go ahead and factor it. So it's looking like 4 and negative 3 might be solutions. Okay? This one over here, start simplifying. bring everything over. So add 5x to both sides, and add 12 to both sides, and factor again. Now with this one, actually, you can't factor it the fast way. So this was one that I had to turn to quadratic formula on, I feel. So, because if you're looking for factors of 12 to make 9, none of them do. A 1 and a 12, a 2 and a 6, a 3 and a 4, none of them get you to that 9x. So off to the side here, I did do quadratic. So negative b plus or minus b squared minus 4ac all over 2 times 1. Simplify. We get 81 plus 48. Actually, it's a negative 48, sorry. Negative 4 times 12 is minus 48. Everybody see that there? Nothing simplifies. So a negative 9 plus or minus the square root of 32 over 2 are our other two solutions. All right, now this is one again as far as a time saver. I am going to tell you that when you run a check, putting a negative 3 in here does not work. Okay, so if I end up with a negative 3 plugged in for my x values up on top, I do not get a true statement. The same is true if I plug in a 9 minus root 33 over 2. So negative 9 minus square root of 33 over 2, 2, also doesn't check. So there are only two solutions in the end to this one. The 4 worked and gave a true statement, and the negative 9 plus root 33 over 2 as well. That second one, that's a rough one to figure out for extraneous. You got some math behind checking that one through. All right, so these last two questions are application ones, so we've got some story problems here. I decided I wasn't going to retype all of the checkpoint problem at the bottom of 126, so please turn there so that you can read along with that problem with me. The problem right above it, example number 8 from the textbook, is very similar to this. But it says a high school charters a bus for $560 to take a group of students to an observatory. When 8 more kids join the trip, the cost per student decreases by $3.50. How many students were in the original group? All right, so let's have some facts listed out here. First of all, our cost is $560. Okay? That was for original amount of students. Okay, we had X students. Now we had a new group because 8 more kids decided to come along. So our new group, again, we didn't know what the original one was, but our new group is going to be 8 bigger. Okay, so represent it with this expression. Now if you were going to figure out the cost per student initially, okay, if you had $560 for the trip and you had X number of people going, do you guys agree that your original cost would have been that total divided by how many went? Okay, so in this story problem it tells us that the original cost was reduced by $3.50 per person. So take the original cost per person and show that deduction of $3.50. All right, so sit back and just take a look at this information and see if you can digest where these expressions all came from. If you can't, that's something that we should probably discuss as a group when we come back together. Now, if you were going to figure out a trip, it's the number of people and the price per person, agree? So here's our actual number of people that went, and here's the actual cost that it was going to cost each person to go. So if I multiply those two together, I should come up with that trip cost. So the number of people the new cost per person, and that will total up the $560 that the trip is going to cost. All right, so now we have to do our math. Okay, there's quite a number of steps here. So let's go through this a little bit at a time. The first ones, I have to FOIL. I've got two binomials, so I have to FOIL them together. So x times 560 over x is 560. Outside, I have negative 3.50x. Inside, I end up with 4480 over x. Okay, that's my 8 times my 560 over x. And then my last one, the 8 times the negative 350, is negative 28. And I have that 560 over here. Okay. Now, with this one, I'm going to do a little simplifying here. Do you see that you have a positive 560 on both sides of your equation? Whether you take care of this now or you find that it's going to go away in the future, those are going to take each other out. So I'm going to just bring it down a little bit. To that. That x is in the denominator. In order to get it out of the denominator, I can multiply everything in my equation by x. So that's going to make negative 3.50 x squared. This will now just be 4480 minus 28x, and 0 times x is still just 0. Okay. Now my lead term is negative. I'm going to multiply everything through by a negative 1 to change that. So 350x squared. I'm going to bring my x term up next. So I'll put them in descending order here. And now my 4480 is negative. And again, a 0 times a negative 1 is still 0. All right, I went with quadratic formula for sure on this one. So negative b plus or minus b squared, which is 784, minus 4 times a times c, all over 2a, which is 7. So doing the math underneath the radical sign, negative 28, you end up getting a 63,504 in there. I always love it when these turn out kind of nice. The square root of 63,504 is 252. So when I figure out these problems, negative 28 plus 252 over 7 is positive. That gives me a positive 32. If I were to take a negative 28 minus 252 over 7, I'm going to get a negative number. There's absolutely no way to have a negative number of students going. So I'm just going to disregard that other option. 32 ends up being the number of original students, and that's what we were looking for. So lots of steps, nothing overly difficult, nothing that we haven't done in the past. The trick with these is going to be the setting up of all of these pieces from the very start. All right, we talked about compound interest way back in the beginning of the course as well. Now we're going to do a story problem that involves it. The main thing is to understand the formula itself. So what I've done here is I've listed out an explanation or a meaning for each of the variables in it. Okay, so A is your balance or your total. P is the principal or the money that you put in or borrow. The rate is a percent. Don't forget to turn that to a decimal. N is the number of interest periods in a year. Okay, so we talked about that a little bit. If you're going to compound interest monthly, N is going to be 12. If you're going to compound interest quarterly, N is going to be 4, and so on. If it's weekly, I suppose that could happen. N would be 52 then. And then T, of course, is going to be time. Time in a compound interest formula is always in terms of years. All right, so this is the last problem that we're going to go through. This is found on page 127 in your book. It's checkpoint number 9. So a deposit of $2,500 in a mutual fund reaches a balance of $35.4406 after 5 years. What annual interest rate on a certificate of deposit, compounded monthly, would yield an equivalent return? All right, so the information that we have. This is what you put in. That's P. This is your balance. That's A. 5 years of time. Compounded monthly, so N is 12. Okay, the thing that we don't know is R, and that makes sense because they're asking us what interest rate would we have. So let's fill in what we know. Our formula is this. We have our amount. We have our principal. We do not have our rate, but we do have N and we do have T. All right, so we have to start breaking this apart and solving for R. The only thing you can do to start with here is to divide both sides by 2,500. Now dividing both sides by 2,500. If you know how to keep all these steps into a calculator without hitting return and rounding anything off, the better you are. If I divide both sides by the 2,500, I get to here. I think I kept every number that I saw. If you need help keying this kind of thing in, we can take a look at that together. All right, now how do I undo a 60th power? Okay, if I raised my right-hand side to the 1 over 60th power, I would end up canceling my exponent to a 1. Okay, you remember when you raise a power to a power, you multiply those powers together? I need to raise this to the 1 over 60th power so that those 60 and the 1 over 60 will cancel. What you do to one side, you have to do to the other side. Okay, so my right-hand side's looking pretty good because I'm going to have 1 plus r over 12 to the first power now, which is just 1 plus r over 12. This you can key into the calculator on your right-hand side. Okay, so type in the 1.417624, hit the exponent button, and then probably in a parenthesis put 1 divided by 60 or 1/60th in. When you hit return, this is what I see. Check it, try it, make sure you can key it in and get the same thing I have. Now I can subtract 1 from both sides. We're almost there. And now you can multiply both sides by 12. When I do that, I have approximately this number for my rate. Now remember, when you're solving and you come up with R in your equation, R is in decimal form. All right, so in percent form, we're roughly looking at 7%. All right, this is definitely one of those sections that I want to force you to do some practice. So from pages 128 to 130, I am going to have you guys turn in these 8 questions. 96 and 100 are similar to these practice problems that we just did at the end. All right, I want you guys to work through setting up some like this. Number 100 is a compound interest problem like we just did. 96 is similar to our trip where we had to come up with those expressions and so on. So give these a try and have them ready to turn in. We'd have a little bit of work time in class as well.